Hello, this is Analog Circuits 18PC42, Module 3, Lecture 2, Part 1, Output Stages and Power Amplifiers. I'm Dr. Nurullah Sharif C. So we see that the output stages should have low output resistance so that all the output voltage will be delivered to the load without any loss of the gain. This can be explained something like this. You have here a output stage whose output impedance is R0 and you have the load over here, and we can write the output load voltage in terms of the output voltage of the output stage as VL is equal to V0 into RL divided by RL plus R0. The current flowing through this is V0 by RL plus R0 multiplied by RL will give us the value of VL. Now this equation clearly says that if R0 is very much less than RL, this is very small, you can neglect this. RL will cancel and we'll be left with VL equal to V0. So under the condition that R0 is equal to a very small value or negligible value, all this voltage will appear across this. So we see that the large signal amplifiers are used to drive the common ray tubes, cathode ray tubes, loudspeakers, and servo motors. The power amplifiers are also known as large signal amplifiers, and the power amplifier can deliver large voltages or currents or large amount of power. And whenever we talk about the large power, then there's always a possibility that a lot of heat is dissipated, and hence thermal considerations come into picture. So when we are using large signal amplifiers, under that condition we can't apply or use the small signal models. And also we see that whenever large signals are there, then harmonic distortion is an issue because of the reason that the what we call transistors are generally nonlinear devices, and hence there will be some sort of harmonic distortion. Also, we see that for the output stages, the most challenging aspect is its efficiency. Whenever we design the output stage, it is the efficiency which is most important. The power dissipation, when there is a lot of power dissipation, then internal junction temperatures will be an issue. So the power dissipation is concerned with the internal junction temperature. Now we are coming to the classification of the output stages. The output stages are generally classified on the basis of the fraction of cycle for which the input wave is present, or fraction of the cycle for which the input sine wave during which the transistor is going to conduct. So when does the transistor conduct? For what part of the input cycle the transistor conducts? That will decide the classification of the amplifier. So that just means that the for what portion of the input signal the collector current is present. The collector current is present. So we classify them into class A, class B, class AB, and class C. And class A is in a output stage wherein the bias current is greater than the magnitude of the signal current. We bias the output stage in such a way that the biasing current is more than the signal current itself, magnitude of the signal current. So the conduction for this case is 360 degrees. That means for whole of the input cycle, the class A stage will be operating, conducting. Then we come to the class B output stage. This is biased at 0 DC current. The transistors or the device output stage is biased at 0 DC, and the conduction angle is only 180 degrees. So that means For the other half of the cycle, the other transistor will conduct. So we will be using two transistors over here, and in these two transistors, half cycle is conducted by one transistor, rest half cycle the other transistor. Then we come to the class AB output stage. This is somewhere between A and B. So this is biased at non-zero DC current, much smaller than the peak current of the signal. So the conduction angle is somewhere between 180 and 360 degrees. And again, we use two transistors to combine what you call to give the total 360 degree what you call conduction. Now this comes into picture because we have what is known as the minimum VB needed for the transistor to conduct. We see that the transistor needs minimum VB to conduct. So because of this reason, we see that the what you call transistor is made to conduct a little more than 180 degrees because of the reason that the transistor needs more than uh, the cut-in voltage, so to say, minimum value of VB voltage. Then we have the class C output stage where the conduction is smaller than 180 degrees, and here the current is passed through a parallel LC network to obtain the output signal. We see that this is seldom used because there is a lot of loss of whenever we talk about parallel LC network, it operates under resonance conditions, and hence we see that the inductance is there, and a lot of heat is generated, and hence we don't use the class C so much. So class A, B, and AB are used as output stages of op-amp. The class AB amplifier are preferred for the audio power amplifiers, and class A amplifiers are usually used at very high frequencies. They are used very less. So this gives us the whole, conduction for class A, which is 360 degrees. This is 180 degrees for class B. This is class AB, little more than 180 degrees, but lesser than 360 degrees. This is class C, where the conduction is lesser than 180 degrees. Now let us come to the class A output stage. Now generally we see that the emitter follower is the one which is used in the class A output stage because the emitter follower has very low output resistance. And let us see the transistor characteristic of this. So this is how the emitter follower looks like, where we have the constant current source. This is how it looks like. This is the constant current source, and this is the transistor to which we are giving the input voltage. Now we should see that this transistor conducts for all the time for 360 degrees. Otherwise, it will not be operating in the class A configuration. So this should be somehow made to operate all the time. It should be on all the time, 360 degrees. Now this is the transfer characteristic of the device. So IE1 is equal to I plus IL. That you can see over here. This is IE1, that is equal to I plus IL. IE1 is here, I and IL is there. Sum of these two will be equal to IE1. Similarly, the output voltage here is VI minus the VBE. VI minus VBE will give us V0. V0 is equal to VI minus VBE. So IE1 is equal to I plus IL. So Q1 is biased with a constant current I supplied by Q2. So this is a constant current source which is used for biasing purpose, and Q1 is biased with this constant current I. Now this I should be greater than the largest negative load current. That is because IE1 is equal to I plus IL. If we have some largest negative current, this value I should be more than that because of the reason that if only when this is smaller than this, we'll have a positive IE1, and when the positive IE1 is there, then only the Q1 is conducting. Otherwise, Q1 will not conduct. Once it stops conducting, then the what you call output stage, the output and the amplifier will stop operating as a class A amplifier. So therefore, I should be larger than the negative load current. So V naught, we said that is equal to Vi minus VBE. Then the transfer characteristic will be something like this. This is the transfer characteristic. This is the transfer characteristic. So we have the peak voltage, that is the maximum voltage, as VCC minus VCE1 sat. So the minimum voltage which can appear across this transistor will be VCE sat, and at that time we will have at the output VCC minus VCE sat equal to VCC minus VCE sat equal to V naught. Okay, so that is the maximum value. And the minimum value across this will be decided. V naught will the minimum value of the V naught will be decided by two different considerations. The two different considerations are, we will have it can be minus IRL and minus IRL, because of the reason that when we have the what we call minus IRL over here, at that time the current flowing here will be I. Minus I, rather, like this. So this is I and this is I. So when both are I, then naturally IE1 will be equal to 0. So IE1 should be always more than 0. For this to be more than 0, that becomes the limit. If this is, what you call more than 0, then only Q1 conducts. Otherwise, Q1 stops conducting. So that is what uh, you know we mean by considering that the V naught minimum is minus IRL, and that is decided by the Q1 turning off. If V naught minimum is more than this, then Q1 turns off. So it is the what we call limit of this V naught minimum is decided by Q1 being turning off. Or it can be minus VCC by VC sat, which is decided by Q2 saturating. So if Q2 saturates, the Q2 saturates over here, then the value will be across this will be VCE sat, and hence we have minus VCC here. So that will be the value. V naught will be equal to VCC minus VCE sat. That is what is mentioned over here. Minus of VCC minus VCE sat is decided by the Q2 saturating. And that is written over here. Minus VCC plus VCE sat. And the value of I is basically decided by what should be the value of I. I should always be greater than the what you call IL. We already said it should be greater than the largest negative load current. I should be greater than the largest negative load current. And the largest negative load current is considered here as this value. Okay, this value. So we will take here mod of this value divided by RL. I is greater than mod of this value divided by RL. That is because of the reason that we have here, when V naught is there, the value of I should be greater than the negative value of largest negative value of IL. And largest negative of IL is decided by V naught is equal to this value divided by this current. Voltage is this, and this will be the resistance. So if you divide this current by this resistance, you will get the largest negative current, and that will be the deciding factor for I. Now coming to the signal waveforms, the output voltage swing will be from minus VCC to VCC plus VCC if we assume that the VCE sat value is very small. So when we assume here that VCE sat, VBE sat, all of them can be neglected. So under that condition, we see that the V naught will be, we have seen VI minus VBE1. And if VBE1 is neglected, V naught is equal to VI itself. So if VI is equal to 0, then V naught can be assumed almost equal to 0. And the what you call when Vi is equal to 0, V naught can be assumed almost equal to 0. So it will follow, the output will follow the input. So output voltage swing will be from minus VCC to plus VCC. So that because of the what you call so to say the transfer characteristic, if this is equal to 0, this will be plus VCC. If this value is 0, then this will be minus VCC. So output voltage swing will be from minus VCC to plus VCC with V naught equal to 0 at Vi equal to 0. And this is known as when Vi is equal to 0, V naught equal to 0. V naught equal to 0 is known as the quiescent value. And quiescent value means no input signal conditions. No input signal conditions. So the what you call V naught will be this waveform, which is specified by this range. V naught will be this waveform. VCE will be naturally, if you see here, VC what you call V naught will be VCC minus VCE. V naught will be VCC minus VCE. So VCE will be naturally VCC minus V naught. So in that case, when we try to write the VCE as VCE1 as VCC minus V naught, we'll have to subtract from VCC this quantity, and then definitely we'll get this waveform. VCC minus 0 will be VCC. VCC minus VCC will be 0. VCC minus again 0 will be VCC. VCC minus of minus VCC will be 2 VCC, and so on. The figure C shows the waveform for IC1 collector current of Q1. So this is the figure C, which shows the collector current of Q1. Then figure D will show the power dissipation of the transistor Q1, which will be definitely the what you call the multiplication of the VCE with IC. VCE with IC. And VCE value is known from here, and IC value is known from here. So we can try to find out what is the maximum value possible. So from this formula, we can try to find out what is the power dissipation which will occur in a transistor. Q1 most of the time, and even sometimes Q2 also. So when Vi is equal to 0, then we know V naught is equal to 0, neglecting the VC sat and the VC sat. That is the quiescent condition. The power dissipation and in Q1 will be VCE1 into IC1, and when we have VC sat is equal to 0, VCE1 will be equal to VCC itself, VCC minus V naught, and the maximum value of IC1 will be I itself. So Q1 should be able to withstand this continuous power dissipation. So maximum value of IC1 will be I itself, which is the current supplied by the constant current source, and the value of VCE1 will be VCC if we neglect VC sat. So this will be there for a very long duration of time. Most of the time this will be there, and hence the transistor should be, Q1 should be able to withstand this power. So also we see that under the open circuit conditions, that is when we don't have any load or when RL is equal to infinity, when the RL in the circuit becomes equal to infinity. This is infinity, or we call it as no load, or open circuit conditions. IC1 will be equal to IE1 will be equal to I. So there is no IL. IL is not there when RL equal to infinity, and then under that condition, the value of IE1 and almost IC1 will be equal to I itself. So now the power dissipation depends on the output voltage V naught. So what is the output voltage V naught? So And this power dissipation will be maximum when V naught is equal to minus VCC. So when V naught is equal to minus VCC, then we see that the power dissipation will be maximum. So under that condition, you see that PD1 is equal to VCE1 IC1, and VCE1 will be VCC minus V naught. And if V naught is equal to the value of minus VCC, then that will become VCC minus of minus VCC, and IC1 maximum value is the current. IC1 corresponds to the constant current source I. So this will become 2 VCCI. However, this will be for a very short duration of time during which the V naught will be equal to minus VCC. So V naught equal to minus VCC will be very short duration, and hence, you know, this cannot be considered as the what you call the condition for the transistor to bear the load of bear the power dissipation like this. Generally, we bother more about the average power dissipation, which will be 0 at one end and 2 VCCI at the other end, and the average of that will just turn out to be VCC into I. Then we come to under short circuit conditions, which is more of a problem we see than the other conditions. So short circuit condition occurs when RL equal to 0, when the load resistance is equal to 0, and theoretically when load resistance is equal to 0, we will have infinite load current. But practically, because of the output resistance present for the emitter follower, whatever value, we see that the what you call load current will be large, very large, okay, which flows through Q1. Now this naturally should come through the Q1. This might cause permanent damage to the transistor Q1. Therefore, the output stage should have short circuit protection so that it never, is shorted. So power dissipation in Q2 will be also, we see that till now what we saw was the power dissipation in Q1. Now the power dissipation in Q2 will be maximum when V naught is equal to plus VCC. So at that time, PD2 will be VCC minus of minus VCC into I, that will be equal to 2 VCC by I. Again, V naught will be equal to VCC only for a very short duration of time. Therefore, again, we might go for average, value considerations, which is corresponding to this, rather than the 2 VCC I. Now we come to the most important aspect of the output stage design, which is the power conversion efficiency. And the power conversion efficiency is decided by average load power PL divided by the supply power PS. How much of the supply power is converted into the average power load decides the power conversion efficiency. So if the output voltage peak is considered V naught hat, then PL will be the load, average load power will be Vrms square by RL. So the Vrms value will be, this is the peak value, so therefore RMS value will be divided by root 2 whole square divided by RL is equal to 1 by 2 V naught square by RL. Then the power supply value maximum will be VCC minus of minus VCC into I. One side you have VCC, other side you have minus VCC in the figure of the output stage. So you have here VCC plus VCC, you have here minus VCC. Therefore, the maximum supply power will just correspond to the value PS is equal to VCC minus of minus VCC into I, and that is equal to this. So we need to divide this with this to get the efficiency. So efficiency will be 1 by 4 V naught square IRL VCC. So we can just write here V naught by IRL and V naught by VCC. And since the maximum value of V naught should be either associated with this, or you can say V naught is definitely lesser than VCC and V naught is definitely lesser than IRL. We see that both these quantities will be lesser than 1. And when both these quantities are lesser than 1, maximum equal to 1, at that time the maximum efficiency will be 1 by 4, and that just corresponds to 25%. 25%. So that is the maximum possible. So neta here is low. So class A output stage is rarely used in high power applications because the efficiency is very small, and this efficiency is usually between 10 to 20%. It cannot be, this is the maximum value. Generally, practically what we see is it is 10 to 20%. Now let us take some of the numericals associated with this. So here we have for the emitter follower in the figure which we have considered, VCC is equal to 15 volts, VC sat equal to 0.2, VB equal to 0.7, and constant and beta is very high. Find the value of R that will establish. So this we will not find because this is associated with the constant current source, but rather we will try to find out from the other two parts here. So we'll assume RL is equal to 1 kilo ohm, determine the resulting output signal swing and the minimum and maximum emitter current for Q1. So the output signal swing V0 minimum is is from V0 minimum to V0 maximum. V0 minimum is minus VCC minus VC sat, and V0 maximum is VCC minus VC sat. So this will be minus 15 minus one value VC sat is 0.2. This will be 15 minus 0.2, that will be minus 14.8 to plus 14.8, which is given here. Similarly, the minimum and maximum emitter current are associated with the what you call values of this what you call minimum and maximum output voltages only. So the minimum value, the maximum value will be V0 maximum. The minimum value will be V0 maximum plus V0 minimum divided by RL, and the maximum value will be V0 max minus V0 minimum by RL. So if you add these two up, then you'll get 0. And if you subtract this from this, then you'll get 29.6 divided by RL. That will give us 29.6 milliamperes. Then we come to another problem wherein we consider here VCC is equal to 10 volts, I equal to 100 milliamperes, RL is equal to 100 ohms. The output voltage peak is 8 volts sinusoid, and we need to find the power delivered to the load and the average power drawn by the power supplies and the power conversion efficiency. And we are ignoring the VB and VC sat and all those things and loss in Q3 and also R. So PL is equal to V0 square by 2RL, where V0 is the peak value. So 8 square divided by 2 into the value of RL is 100, and that gives us 0.32 watt. PS is equal to 2 VCC into I. 2 is the VCC value is 10 here, and that is written, and the value of I is given as 100 milliamperes, and that turns out to be 2 watt. The efficiency is definitely PL by PS into 100 in terms of percentage, and that will be 0.32 by 2 into 100, that is 60%. So that is what we have here. The next numerical is associated with the value of VCC equal to 10 volts, I equal to 100, RL equal to, again, 100 ohms. Find the power dissipated in Q1 and Q2 under quiescent conditions. And for a sinusoid output voltage of maximum possible amplitude, neglecting VC, find the average power dissipation in Q1 and Q2. Also find the load power. So under the quiescent conditions, we see V0 is equal to 0, and at that time PD1 equal to PD2 is equal to VCC into I is equal to 10 into the value of I. So I is 100 milliampere, that is 0.1 amperes, and hence we'll get 1 watt. The second part is, we need to find the average power dissipation in Q1 and Q2. And for a sinusoidal output voltage of maximum 10 peak volt, the instantaneous power dissipation in Q1 will be according to the waveform which is given in D figure. Thus, the average power dissipation in Q1 will be half of VCC I, that is half of this quantity, and that will be equal to half into 10 into 0.1 equal to 0.5. Then for Q2, the current is constant, I is equal to this, and the voltage of the collector will have an average value of 0, and thus the average voltage across Q2 will be VCC, and the average dissipation will be again PT2 equal to I into VCE average. I into VCC, always I will be flowing through the what you call Q2, and that will be, we'll have zero point 0.1 into 10 equal to 1 watt. So finally, the power delivered to the load will just correspond to V naught RMS square by RL, and V naught RMS square will be 10 divided by root 2 whole squared by 100. That will give us the value of 0.5 watts. So with this, we come to the end of this lecture. We'll take up the class B in the next class. Thank you.